Great, so lastly, we're going to discuss the relationship between translational and angular quantities. So I've redrawn the picture here where we have a point that's some distance r from the center, and then the disk spins some angle theta. So we have already decided that the arc length there of S is going to be equal to r times theta. Again, I'll emphasize it in radians. And so we can then talk about the speed v is going to be equal to ds dt, right? The rate change of that position. And so that's going to be equal to d dt of r theta. So the r for some point is going to be constant, so that's going to be equal to r times d theta dt. And remember, d theta dt is just omega, so that's equal to r times omega. So we can then go through this for each value, and you can fairly easily derive the relationship between the actual translational quantities, which we've learned before, and then their rotational counterparts. And so we end up with some key equations. So the translational speed, which I'll call v sub t, and then put this notation to include the rotational speed, is going to be equal to r times omega. The translational acceleration is going to be equal to r times alpha. And then we even have this idea of our centripetal acceleration, right? Remember that the centripetal acceleration was equal to the translational speed, v squared over r, and now I'm just putting the subscript t to keep them clear from each other. And so that's now equal to r omega squared divided by r. So this equals r omega squared. And so these equations are very useful, as we'll see, and we'll come back to them here and there in problem solving, because you have a direct translation between, say, a point on a rotating object and what's happening in terms of its center of mass, its translational motion, and what's happening in its angular motion. All right, that concludes our pre-lecture video. If you have any questions, let me know.